Hello, everybody. I'm looking forward to arriving in Arizona tomorrow. We're getting on a plane tomorrow morning Eastern time, so very early in Arizona time. And yeah, we'll see you next time for the lecture in person and questions. I really look forward to it. Can you see my screen that it says Moore's Law and beyond? Can you hear me clearly? Let me know if you can't, I guess. All right. So before getting into the quantum aspect or the quantum frontier of physics and computing, I want to finish up the circle of ideas we talked about last time. And this leads logically into why we are forced to think about quantum mechanics in computing and why it is the logical next step. But also for students and people who want to contribute to the frontiers, I'll point out, sketch out where we are today, so you can see where we might go tomorrow in directions other than quantum computing that look promising. So Moore's Law is a famous prediction of Gordon Moore, one of the pioneers of modern semiconductor technology and one of the prime movers in the early history of the Intel Corporation, where he noticed, I believe in the late 60s, so before this graph even begins, that the density of transistors and also other measures of computer performance were doubling every 2 years. So the number of transistors was doubling, the speed, the density, so the chips weren't getting bigger physically, in fact, they're smaller. But this is an extraordinary thing. It's very, very unusual to be able to maintain exponential growth for 25 doublings. I can think of few other examples in technology or in history or even in biology where you may see population explosions, but not for 25 generations. Maybe the best example is the growth of an adult organism or an infant from an egg. You get 25 doublings. But for a technology, this is really an extraordinary thing. It's not an accident that this doubling occurred, because the semiconductor industry used this as a benchmark for what they should try to be attaining year after year, and getting their salespeople and software engineers ready for what was coming. But that they've been able to hit this benchmark over and over again is just extraordinary. And this is what a modern central processing unit chip looks like. It has trillions, oh, not trillions, billions of transistors on it. And it's something that is roughly the size of a fingernail, or at most, it fits comfortably in the palm of your hand. Let's look at this more quantitatively. The clock speed means the number of operations that it performs per second, roughly. There's some parallelism, so actually this is an underestimate of the number of operations, but it's the number of turnovers of the program, if you like, is 3.2 gigahertz. That means 3.2 billion operations per second. That's compared to the rate of firings in an animal or human nervous system of roughly 40 per second. So the computer thinks much, much, much faster. And the price is Also remarkably low considering what it is. The mainframes of the 1950s were room-filling beasts that were millions of dollars in contemporary funds, and really were only bought by government research agencies and defense contractors. Whereas now, $999 is something that in principle, many people can afford easily. However, there are a couple of other things to notice here that will be the theme that we'll take up. That is that this little chip, small as it is, uses 130 watts. So it's comparable to a little more than an old-fashioned light bulb, which, as you know, if you've ever tried to change a light bulb, they get very hot. And the other thing to notice here is the physical size is 45 nanometers. The physical size of the features on this chip, so the individual transistors, roughly speaking, are 45 nanometers on a side. This compares to the size of an atom, which roughly speaking is 1 or 2 nanometers, and a respectable molecule is at least 10 nanometers. So we're getting very hot and very small. Heat is becoming a big problem. I'll show you that pictorially in a moment. And sizes are getting down to a molecular level. So the days when you could ignore the fact that matter is made out of molecules and treat the matter as continuous solids, even using the methods of quantum mechanics, is rapidly coming to a close. So here is a dramatic illustration of the heating problem. This is one of Facebook's data centers that is opening up in Luleå, Sweden, which is above the Arctic Circle. If you look inside, it's got these enormous fans to cool things off. It also, well, I think the real reason that they have it up there is that it's big and the land is cheap up there. But in any case, you get a little help with the cooling just by being up above the Arctic Circle, which this is. Here's the basic physical issue that dictates, that is the hang-up here to making further progress, because obviously if things are getting that hot, they get very difficult to cool. If you want to pack a lot of these chips into a small space, it's like you're packing an enormous number of incandescent lights, but miniature incandescent lights into a small space. It gets very, very hot indeed. And things start to melt or misfire. And here's where that comes from, why that arises. The bits that are used in semiconductor technology are buckets of electrons that are held at 2 different voltages that represent the zeros and ones. So let's say it's plus or minus some voltage divided by 2. And typically this is, for those of you who know something about band theory, this is in the conduction band or the valence band of the semiconductor separated by voltage V. If you have n electrons per bucket, okay, so to have reliable operation, n should be at least a few. When n gets to be of order 1, you have to start to worry about noise of all kinds, including quantum mechanics. Anyway, when you have n electrons per bucket and a switching time tau, remember this was the gigahertz thing, and people want their computers to be fast and they want to want them to perform a lot of operations as fast as possible so that you can do searches or crypto or mining in crypto or whatever. You want things fast, and if the power consumption to move things fast through a voltage V is the energy that is changed when you change a 0 to a 1 over here. You do it for all of the n electrons, and you do it in a short amount of time, so that's the power, energy per unit time. And the time is related to how long the signal takes divided by the distance, so you can also say that making it smaller is a good thing, but also it leads to problems because the heat gets large. So the heat, this is compensated by the fact that you have L squared units in a overall dimension L, but I'm sorry, big L divided by little l squared if their overall dimension is L. So having things small is a good thing. You can have more transistors, but you also generate a lot of heat. So when you get to n equals 1 and atomic dimensions, which is where we are today, you're getting close to n equals 1 and atomic dimensions, as I showed you. Those two things go together because when you're that small, you don't have a lot of electrons per unit area. The only thing left to push on is V. The only way you can get this to be smaller is to make it V, is to minimize V, because N and L are basically already pretty much as small as they can be. Current technology is based on the energy gap of silicon, which is 1 volt. With more exotic semiconductors, it might be possible to push that down to about 1/40th of a volt. So there's an extra, there are perhaps a few more generations of Moore's law to be gained this way, and you can nickel and dime the other factors. But with more exotic semiconductors, you need different kinds of manufacturing plants. It's very expensive. This will be difficult to do. A lot of knowledge and optimization and building of foundries have gone into the silicon technology. And even so, if you got to 0.025 volts, that's basically room temperature. And then unless you want to bathe the whole thing in liquid nitrogen or liquid helium, you're kind of stuck. And if you want to not only get things that cold, but keep them cold in the process while they're making so much heat, you've got another problem. So it's going to be very difficult to maintain Moore's law very much longer. So there are different possibilities for getting around that problem that are frontiers of physics today and are very important things for physicists who want to make a difference in the world and engineers to study. One is the possibility of using electron spin and magnetic field instead of charge and voltage. This is called spintronics. So currently the bits are, as I said, are based on moving electrons, or more specifically, the charge of electrons back and forth through voltages to get your zeros and ones. Instead, you could move electron spins in magnetic fields, and that requires much less energy and would heat things up much less. You can also use photon polarization for your zeros and ones. I'll talk more about that momentarily. And photons also interact much more weakly than under ordinary conditions than electrons do, because photons are electrically neutral. So photons interact with each other very, very weakly. And using photon polarization is another possibility, where weak interactions go together with small energy dissipation. However, weak interactions also make things more difficult to manipulate. So this is a challenging thing. Another possibility is to use the states of individual molecules, and I'll be saying more about that, but this requires, this is a frontier of technology that it is sort of at the border between chemistry and physics that is under development, and we don't know how to do it in any case. It's, we don't know how hard it's going to be, but it's certainly not easy. Or you can use superconductivity. Using superconductivity, of course, superconductors require things get cold, but so you'd still have to be putting, if you want to go the superconducting route, so still based on charge, roughly speaking, or manipulating charges in circuits, that you still have to keep it, you make it cold because superconductivity is a low temperature phenomenon. However, the superconducting circuits, once you make them cold, they don't generate a lot of heat. So that's a promising direction as well. So these are all under consideration and are being actively pursued in research laboratories, but as yet, they're not yet competitive general purpose technologies. And there's a lot to say about each of those things, but in the nature of this survey, I won't be going into the details of that. I'll be very happy to supply references for anyone who wants to pursue it further. Now, an interesting observation to put things in perspective and maybe open up the consideration of more of the quite different kinds of technologies is that a human brain runs at roughly 30 watts, which is roughly comparable to a laptop. So it's rough. What I showed you earlier was a high-end chip that ran at a small multiple of 30 watts. I think it was 130 watts. An ordinary laptop takes about 30 watts. You can hold it in your lap, and your lap starts to get warm, but it doesn't usually burn up your pants. But a human brain, which is certainly in its own way as capable as one of those CPUs or a laptop, doesn't generate nearly as much heat, or per capability, so to speak. It runs relatively cold for its size and intelligence. So that kind of soft engineering, where things are not put together electrically, but out of soft materials, which are relatively slow, but can be interconnected in much more complicated ways, may be a different way to do engineering in the future. The science fiction writer Olaf Stapledon anticipated the idea that through genetic engineering, if you want to make the computers of the future, or the minds of the future, they could look like giant brains that would scale up neural architectures as opposed to transistors. So this is a fascinating idea, the whole idea of a new form of engineering based on self-reproduction with variation. And I think it's an underexplored area for the future, but at the moment is more in the mind of science fiction than a practical program. So getting back on the ground, we're getting to the point, as I've shown you, where quantum behavior of our bits is becoming a serious issue. We're getting down to the scale of single electrons and the distance scale of single molecules. So we can treat that as a problem, and it is a problem because you have to worry about the effect of quantum uncertainty, quantum fluctuations. Do those things mess up the functioning of your circuit? When you have one electron, can you really make sure that it's where you think it is, or where one electron is not so different from none, and numerically, and so you better be sure you know where it is. And quantum fluctuations get to be a problem if you don't. Or we can rethink the whole thing and take this quantum behavior as an opportunity to have a different envisioning of what information is and what we want to do when we compute. So that leads into today's main subject, quantum bits. So I'll be showing you the foundations of an ongoing revolution in technology called the second quantum revolution. So I'll talk about two things today. I'll tell you what a quantum bit is, and I'll show you quantum bits in action. And then I'll talk about the prospect of quantum simulation. Next time, I will talk about the issues of entanglement and actually using quanta for computing as opposed to simulation, and the possibility of using topology to avoid errors, which is a very big issue. But so we won't exhaust the subject today, but this will give us enough to fill the time available today, and I think will I hope pique your interest for next time. So, what are quantum bits, and what do they do? So this, in the next few minutes, I'm going to show you the essence of quantum theory made simple and concrete. Simple comes with an asterisk because it is fundamentally simple. However, it's unfamiliar. You have to think different, and it's simple but paradoxical. And many people, including Einstein, have had trouble with coming to terms with this behavior. However, it is the way the world works. So I'm going to talk about something that, if you know a little bit of physics, will be, I think, very familiar. If you know about the behavior of polarized light, you'll be perfectly prepared for this, but I'll try to make the discussion self-contained. The propagation of light through polarizing filters, the polarization property of light, can be understood, in quotation marks, using classical concepts, but the classical concepts are wrong. Light is not made out of electromagnetic waves at the deepest level, or that's an incomplete picture of what light is, as Einstein taught us, and many, many experiments have verified since. When you analyze light in detail, when the light gets very weak, when you look at its smallest elements, you find that it's not continuous, that it consists of packets called photons. And when you rethink this phenomenon of polarization and the action of polarizing filters, and realize that it's not something that only applies to waves, but also has to apply to photons, you'll see that it contains the essence of quantum behavior. And in particular, the essence of a qubit. Polarized photons are qubits. They're maybe the most familiar kind of qubit, if you know about polarized light. Okay, so this is the classical picture of what a light wave is. Okay, this is a light wave moving in the direction of this vector k. So following that arrow. It's what's called a transverse wave of electric and magnetic fields. That is, at a microscopic level, what a light wave is oscillating electric and magnetic fields, and they oscillate in space like that. And this wave also propagates at the speed of light forward. So it oscillates both in space and time. This pattern moves along at the speed of light. That's what, so this is light polarized. We say this is light polarized in the X direction. Okay, the light ray here is moving in the Z direction, if you label the axes X, Y, Z. So one solution of the electromagnetic equations of Maxwell, one possible form of light, is where the electric field points always in the X direction, oscillating in magnitude and even sign as it goes along. Of course, we also have, because everything is rotationally symmetric, we can also rotate around the direction, and we have the possibility, we also have legitimate solutions, legitimate forms of light in which the oscillations are in the Y direction. Now, polarized sunglasses are an example, a familiar example, I think, to all of us, and especially to people in Arizona, of a physical phenomenon of the possibility to have filters that filter light and select a particular polarization. So inside this material, if you have a filtered material, a polarizing filter, the electrons only want to move in one direction. So the electric field can only get through if it's pointing along that direction. Basically, these things have long molecules with only one easy direction for electronic motion. And so they only let one kind of polarization of the light through. Okay, so if we start with an incident beam here, which has electric fields oscillating in all possible directions, and the natural sunlight had radiation from the sun that has where the atoms are moving at random, and so they radiate in all different ways, and then it reflects, bounces off things, and you get glare and so forth. So the light comes in with different kinds of polarizations, but the filter only allows one direction of polarization through. So it screens out some of the light and the intensity is reduced, but the light that gets through is polarized in a very definite direction. If you had a second polarizer in the perpendicular direction, then nothing gets through, because only the part of the light that's in this direction that has polarization in this X direction has gotten through the first filter. The second one only wants things in the Y direction, but it's in the X direction, and so nothing gets through. So that's what's called crossed polarizers. Okay, so the filter selects or projects onto the part of the incoming wave that oscillates in its preferred or allowed direction. And what we say in classical optics, or in electromagnetism courses, when we talk about this situation, is that when the polarization of light is off from the preferred direction of the filter by theta, then the filter only picks out the part of it that is in the right direction, is in the correct direction. And so it picks out only part of the oscillations. And therefore, the intensity of the light getting through, if it's not quite in the X direction, but off by an angle theta, so just rotated from X direction towards Y by an angle theta, then the intensity is reduced. It still gets through only in the X direction, but less of it gets through. The intensity is reduced by a factor of cosine squared theta. So when theta is 0, this is 1. When theta is 90 degrees or pi over 2, this is 0. And in between, you get something in between. But, so that's the classical description. But if you think about photons, that kind of very reasonable thing really starts to seem very strange, because photons don't get divided up. They go through whole or not at all. They're photons. They're the particles of light. They're the units of light. They can't be made smaller. So how does the intensity get reduced? Well, this is the essence of quantum theory. In the quantum version, what happens is that photons get through whole, but they get through only with a probability. And the probability is cosine squared theta. So if you have lots of them, the proportion that gets through is cosine squared theta. And that means the intensity, the sum of all their energies, is reduced by the factor of cosine squared theta, but it's still photons. It's just that only a portion of them have gotten through. And so you can have, for instance, this weird behavior. Now, if you don't have this intermediate polarizer, that's the situation. So these dark bands represent the preferred direction of the polarizers. If we don't have this middle one, we don't have the middle one. We have the situation I showed you in the previous slide, where you have one that picks out the x direction, the other picks out the y direction, and nothing gets through. Okay, that's fine. However, if we put one in the middle that's off by 45 degrees, say, then half the light gets through here, and then half again gets through here, because the mismatch is 45 degrees and then another 45 degrees. So you project out half each time. So by putting in an extra barrier, if you like, the intensity goes from 0 to 1/4. Now, if you think about the waves, that's not so strange. The intensity goes up because the waves can adjust. But if you think about photons, it's really weird, because it means that those are particles that couldn't get through before. You put in an extra barrier and now they can get through. So this is an example of the weirdness of quantum mechanics. And if you think about it too hard, or think about it in the wrong way, or think you know what the answer is going to be without actually thinking quantum mechanically about what the theory predicts, you will get very confused and think and get wrong answers, because your intuition doesn't do justice to this situation. However, that's the way the world works, and people who practice quantum mechanics learn by working out a lot of examples to get correct intuition. And the way that you do that is to calculate the predictions in many circumstances and see how they work, get familiar with it, or to put it rudely and shortly, you shut up and calculate. Okay, so what does this have to do with bits? Well, we could use the two polarization states of light to represent 0 and 1. We have two distinct states that are physically completely distinct. We say they're orthogonal to each other. They're literally orthogonal in the sense of directions. And we can use those possibilities, which are entirely different. One passes through a filter, the other doesn't. The right kind of filter, one will pass through with probability 1, the other with 0. So these can be used to represent bits. And however, we also have the weird possibility, which we don't have for ordinary bits, that we can also look at things which are off, or mixtures of these two things. So we can have things that are polarized and photons that are polarized in a different direction, if you like, or just superpositions of the electromagnetic waves that were mixtures of these two things give us things that are mixtures of 0 and 1. So if we interpret the direction of photon polarization as our bit, we have a new possibility that we didn't have for classical bits, which are either 0 or 1. The photons give you bits that can be superpositions, can be mixtures of 0 and 1. You can also get fancier things. This is what's called circular polarization. This is what you have if you have oscillations of the this is showing the electric field. If you have oscillations that are both in the X and Y direction, but out of phase, a little out of sync, then the total direction in the XY plane rotates around as the wave progresses, and this is called circular polarization. So photons and their polarizations are the archetypal qubit, pronounced qubit, meaning quantum bit. Quantum bits are things that have not only states of 0 and 1, but also mixtures, or as we say, superpositions that hang together. Okay, individual photons have some polarization or some polarization state or other, but in general, it's not a 0 or a 1 if you've chosen the X and Y direction to represent the two possible linear polarizations, but the states of photons can be mixtures of the 0s and 1s that are represented in the form of the underlying electromagnetic wave that the photon embodies. So these are organic mixtures, if you like, of 0 and 1. And by manipulating those mixtures, you can do things that you can't do if you have only separate 0s and 1s. If you have bits that are either 0 and 1, but never organic mixtures of the two. So that's what qubits are. Now, polarization expresses the spin of photons when you analyze it more mathematically. In fact, the circularly polarized photons are ones that have definite spin in the direction of motion. And depending on whether the rotation in the XY plane is clockwise or anti-clockwise, you have what is called left-handed and right-handed polarization, and those are the two representing the spin up or down of photons. Electrons also have spins, as do many atomic nuclei. Spin is a fundamental property of elementary particles that also builds up in particles that aren't elementary, like nuclei, because they incorporate the spins of the things that make them up. So, and spin is just what it sounds like. They're rotating, but the amount of rotation is very, very small. And when the amount of rotation gets very, very small, the behavior of the spin is very unusual and differs from classical expectation. We call it spin, but yet it's the same thing as angular momentum. It's just a very small unit of angular momentum, and elementary particles have the property that their spin never vanishes. They're always spinning in one direction or another. So you don't have to put energy into making them rotate. They want to rotate. Now, a very useful aspect of the spins of electrons and nuclei, basically because they are charged particles or have charge distributions inside them, is that these spins are associated with magnetic fields. Okay, rotating electric charges are associated, generate magnetic fields. And they have, in fact, dipolar magnetic fields. Similar, this is very similar to what you would see if you had the Earth. Okay, E could stand for electron. It could also stand for Earth. If you have a rotating Earth, it generates a magnetic field, and that's that phenomena in the microcosm is an observed property of electrons. And it's very handy because these magnetic fields allow us to manipulate and to read out the behavior of electrons using electromagnetism. Okay, you can expose these little compass needles, if you want, to external magnetic fields, and they'll move, or you can sense the direction of their spin by measuring the magnetic fields they produce. Now, the details of that are very interesting because you're dealing with very, very small quantities of magnetism, and the spins are very interesting objects to manipulate, and you have to and delicate, and but basically that gives us a way of manipulating and reading out this spin property, and therefore makes spin up and down a very, very nice kind of bit. Spin up in some direction can be called 1, and spin down can be called 0, and then you have a nice bit. And these are quantum bits because just the mathematics is exactly the same as the polarization of light. It's usually presented in a way that is more intimidating, using complex numbers and spinners, and that's very handy if you want to actually become a quantum mechanic and learn how to work with these things. But if you want to have intuition about it, or if you just want to know what's going on in a general way without mastering that mathematics, you can think about polarized light and you won't be missing anything, because it's really the same situation. But whereas the spin of photons is kind of hard to read out, the spin of and manipulate, well, no, not impossible, but the close connection of electron and nuclear spins with magnetic fields allows us to manipulate and read out their directions much more conveniently. And that's a gateway into the quantum world. So this is what happens when you get magnetic resonance imaging done in medicine. You manipulate the nuclear spins typically by using magnetic fields in those big hospital magnets, and those spins radiate when they're being manipulated, and their behavior reflects the environment they're in, and so you can get pictures that tell you about where the electrons are telling you about the environment they find themselves in. And when you analyze the radiation fields, you can go back and get a picture. It's really the same phenomena at a suitable level of abstraction as using light to diagnose the properties of things we see. We scatter electromagnetic radiation off the objects, and that tells us the properties of those objects, whether they're rough surfaces or shiny surfaces, and something about the chemistry of what they're made out of. And it's a very similar process here, we're just using forms of interactions of electromagnetism with matter that allow us, that are that go deeper and into and allow us to access insides of things that would be otherwise inaccessible. Okay, so now let me talk about quantum simulation. And perhaps the best way to think about this is by analogy. This is a brilliant prospect. By analogy, let me make an analogy to the development of aviation and aircraft design. So a lot of experience was gathered in experimentation, going back to analogies with birds or the more systematic work of the Wright brothers, and so and then these pioneers of aviation and their successors experimented and made designs and things that worked. Like the old biplanes and things, but gradually got more efficient designs and better ones. And then started doing, in order to do even better, started to get more systematic, using wind tunnels to make models and study the behavior of models, as opposed to building a whole airplane. You build a small scale model and analyze the behavior of wind tunnels before building the real thing. And this is much more flexible, allows you to experiment and so forth. You don't have to put pilots in here. You don't have to actually build gigantic objects, and you can learn a lot about design by making things like that. But nowadays, wind tunnels are, for aircraft design, more or less obsolete, because we have simulators of the second kind, where we just compute the behavior using the laws of fluid dynamics and aeromechanics to figure out optimal designs. We see how the different shapes will propagate through air. Now, that's a great thing, and has led to enormous progress in aircraft design. It's much more efficient, and some very, very odd looking wing designs have turned out to be correct, and you never would have guessed them. And okay, so that's been a great success story. However, if we want to do a similar thing for chemistry or for materials, we have to use different kinds of equations, namely the equations of quantum mechanics. And Richard Feynman, who emphasized this already back in the visionary statements in the late 1950s and early 60s, said that nature isn't classical, damn it. And if you want to make a simulation of nature, you'd better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look so easy. And sure enough, it hasn't been easy, but we're making enormous progress along these lines. And in recent years, it's become it's starting to become a reality that you can do quantum simulations in the quantum world. So qubits, which could be polarized light, or more practically electron spins or nuclear or atomic spins, as I've said, capture the essence of quantum behavior. They allow you to have not just zeros and ones, but mixtures of zeros and ones that are organic and allow you to process in parallel zeros and ones, a mixture of zeros and ones. So you can be processing both possibilities at once when you deal with qubits. Now, But also, if you're trying to simulate, if you're trying to reproduce the behavior of quantum mechanical objects, if you build your wind tunnel, so to speak, build your model out of quantum mechanical objects, then you can reproduce the behavior. So this is what's called a quantum simulator, is something that uses objects that obey the laws of quantum mechanics and tries to arrange that their interactions have the same relationship as the interactions of the material or molecule you're actually interested in, but you can manipulate them in a more convenient way, making a kind of quantum mechanical wind tunnel. So that's what I call, so the development is roughly in parallel. People have gathered a lot of experience in designing molecules and materials semi-empirically. And this is what fills books of chemistry and biochemistry. And now at the frontiers, people are building simulators of the first kind for chemistry, where you have the possibility of dialing which kinds of substances you have and how much and on what temperatures and so forth, and do that in a systematic way. This is a kind of wind tunnel, but for chemistry. However, this is still kind of awkward and doesn't get to the essence of controlled quantum theory. You're still dealing with smelly chemicals and big flasks and so forth. A quantum simulator of the first kind, where you have your quantum mechanical objects simulating other quantum mechanical objects, looks like this. Here we have what I call a cold atom wind tunnel, where you cool atoms so they're very, very cold and start to behave quantum mechanically, where the fluctuations in the noise because of their thermal motion doesn't wash out the characteristic quantum fluctuation. So the quantum fluctuations are the dominant kind of behavior when you make them cold. So that's the behavior you want to capture, because that makes them look like they're on a much smaller scale inside individual atoms or molecules. So that's done by having lasers, crossed lasers that make traps, and the atoms want to sit in certain places where the waves of these two lasers have minima, and you can put different kinds of atoms in different places and manipulate their spins and with other lasers, and this makes what's called a cold atom simulator, where you can simulate the behavior of any exotic quantum mechanical material you like using cold atoms. You can also go from simulation to computation. So this is what I would call a simulation of the second kind, where you don't try to reproduce the interactions, but do the analog of purely computational solving the equations of quantum mechanics, exploiting the fact that these qubits obey the same kind of equations as quantum mechanical variables to operate with them. As in a computer, you operate, an ordinary computer, you operate with gates in order to do logical operations. Here you sort of implement the gates by external operations with lasers. The details are complex and under development, but this gives now is a sort of a general purpose quantum computer working on qubits as opposed to bits. And the state of the art is fairly well represented here. Whereas classical computers, as I showed you, can have billions of bits for $999. The top of the line quantum computers of this kind have at roughly a dozen qubits and have to be manipulated in rather awkward ways. So there's a ways to go, but we're on the early part of the Moore's curve for quantum simulators. So let me summarize. Semiconductor technology for computing is great and continues to improve. The epic story of Moore's law is one of the great human and scientific triumphs. But it's starting to bump up against fundamental physical limits. Polarized light, when you interpret it as photons, exemplifies a strange new kind of two-state system, not a bit, which has two discrete possibilities, 0 or 1, but a qubit, which has the possibility of combining 0 and 1 in controlled and rich ways. The same qubit mathematics applies to other quantum systems. In fact, it's the general kind of quantum system. Particle spins are governed by the same principles and are usually associated with magnetic fields, which allows them to be manipulated and read out, so allows them to become the elements of an emerging technology, or of existing and emerging technologies, I should say, that exploit the quantum mechanics of qubits or spins. And quantum simulators could become, for chemistry and materials design, an important supplement to conventional experimentation. Just as wind tunnels were an important supplement to aerodynamic experimentation, and eventually became not just a supplement, but a substitute for experimentation. So it's an inspiring prospect to put chemists out of business, or putting it a different way, to helping chemists do even more advanced projects than they do today. But the bad news is that working with qubits tends to be very delicate. We're talking about individual spins, and when we want to control the interactions of the spins to do actual calculations, I mean, to do gates, if you like, to do logical operations, as I discussed last time, or to do detailed quantitative simulations of particular materials, where you have to tune the interactions or deal with the quantum mechanical equations, which are quite complicated, then you need many qubits and great control. And the bad news is that working with qubits tends to be very delicate, especially if you want to orchestrate many of them. And we'll discuss that issue and how it's being addressed next time. So the issue of how you use concepts like entanglement to do non-trivial, useful tasks, and the limitations of current technology, and a possible way out using topology will be our topic next time. So look forward to actually seeing you in Arizona next week. Bye for now. So, Anne? Okay, that concludes the lecture part. Of course, I'll take questions if in the chat. We'll address them next time, or you can otherwise we're going to adjourn with students into a chat room and take questions from this and discuss with the students.
Frank,
So next time we'll have a discussion.
If you like, Peter Bennett here.
Peter, yeah.
Yeah, thank you for a wonderful lecture. It just reminds lesson, I guess. It reminds me, what is the famous, if you think you know, understand the photon, you don't know enough about it. And you're helping us with that. I have mostly a comment. You might be aware that the department purchased a beautiful demonstration kit for entanglement with the from the QU Tools company, and we have that working in our lab. And I'd be delighted to show that to you when you get into Phoenix.
Okay.
It's the parametric down conversion. You split the blue into two reds, and then you have coincidence counting, and we do the quantum eraser with a Michelson interferometer. What else do we do? We do Hongu Mandel, the dip there. It's amazing. It all works with fiber optics on open daylight on your desktop. It is an amazing instrument. So yeah, the comment, we're going to use that in our teaching labs and for demos, and we can coach you to do a demo if you like. It's
all right. Maybe
amazing.
We'll have to discuss the logistics of that, but yeah, it would be great to do some actual demonstrations.
It really is. The
polarized,
thing is, you can look at this cross Polaroids and things like that, and you did a great job with that, but there's nothing like having it in front of your face and counting photons and where did they go and which way did it go through the beam splitter, just in front of your face. So just a comment there, but we have.
Yeah, I would love to, maybe we can arrange the logistics of that. That would be marvelous.
Indeed, yeah.
But yeah, yes, you don't have to take my word for it. You can actually see these things in reality, and it's quite, how should I say? It's almost a spiritual experience. I found as a theorist to actually see these equations embodied in real life.
Well, that's because you know what it means.
Paradoxical behaviors. Yeah.
Yes, right. If you think too hard, if you think hard about it, it's really quite amazing. Yeah.
Yeah.